So, so now let's start. Thank you for the introduction for Dr. Pam. I'm Hui Zhong. I'm from University of Houston. Today our topic is about content computing privacy and network optimization. And my advisor is Dr. Miao Pan, and my committee member is Dr. Han, Dr. Fu, Dr. Fan, and Dr. Lorenzo. Okay. So here is our outline. So first, I will give you the brief introduction and motivation of the content computing, and then it's my three works. Okay, for the first work is about the first work is about the privacy protection in distributed content computing. So I propose the quantum mini differential privacy. And for the next two work, we are focused on the distributed content computing optimization. And one is well unified nonlinear integral programming, and one is well GNN attention and reinforcement learning. And finally is our future work and conclusion. So let's start. First, I will give you some background about quantum computing. So we can see here is a table show the difference between the quantum computing and the classical computing. Okay, like quantum computing is calculated with qubits. We can see qubit 0 and qubit 1. But for the classical computer, we are really familiar with that. It calculates with bits. Okay, bit 0 and bit 1. And compared with the classical computing, quantum computing, it has the exponential speed and also have the higher error rate. And one of the important things is that compared with the classical computing, the quantum computing has the exponential speed to solve the large tasks. The reason is the quantum computing has some quantum characteristics which will let it has the ability for the parallel computing. Just to give an example, okay, so for the classical computer, it can only be in one of two states, like 0 or 1, which means it can represent only one state at a time. But for the quantum computers, it can simultaneously in the superposition state, like phi equals alpha qubit 0 plus beta qubit 1. So there it can represent many states at a time. So it will have the higher speed. And then I will show you like what the quantum computers really looks like. And there are many famous companies like Google, Microsoft, D-Wave, IBM. And also I give you some applications of quantum computing. We always think it is a theoretical things, but in the past few years, okay, it has been like some practical applications in the cryptography, drug discovery, and optimization problems. So I give you some famous companies. Like for example, the Protein Q, it is a company for the medicine. So they will use the quantum computing to help analyze the protein and then find the medicine to like prevent the cancer. And there are many types of quantum computing, like quantum annealing, photonic quantum computing. And in our work, we focus on the digital quantum computing. So then I give you some background about digital quantum computing. The first thing is quantum gates. So we can see it is a basic operations in the digital quantum computing. We can see there are some examples like single qubit gate, poly X, poly Z, and Hadamard gate, and also some two qubit gates like CMOS gate. And the second column is notation. So if we want to draw the gates in the circuit. And the third column is matrix. So if we want to do some calculations in the quantum circuit. So then if these gates are at a special sequence, and then it will construct a quantum circuit. So here just an example to show what a quantum circuit looks like. So this is a 4-qubit circuit, and we can see there are many gates. And I know it's still a little abstract, so I give you an example to show the whole process, how quantum computing can like calculate. So now we have a quantum state input. We assume that here is rho and here is its matrix. And then we can see if we pass through, now the rho pass through the circuit has an X gate. The rho will then turn to the rho prime, and here is its calculation. So because we cannot directly observe the quantum state, so then we need to use a measurement to collapse the quantum state into the classical output. For example, if in this circuit we use the poly Z measurement, like N0 operator and N1 operator. So then finally we can get two classical outputs, 0 or 1. So the 0 probability is 40% and 1 probability is 60%. So now if we do this circuit 100 shoots, which means like we do this circuit 100 times, then we can get the expected result. The 0 is 40 times and 1 is 60 times. And also I will show the digital quantum computing history. So here is a map shows the number of qubits for one QPU. We can see like 2019, for one QPU, there's only 27 qubits. But for 2025, we can see it's extended to about 4,000 qubits. And the researchers call this current state is noise intermediate scale quantum technology, the NISQ state. But we can see one of the challenge is it has limited qubits per QPU. Although now it has 4,000 qubits for one QPU, it's still far less than the classical computers with millions of bits. So for the future work, researchers want to move from NISQ state to the fully error-corrected quantum computers with millions of qubits, but it takes much longer time. So why scaling is difficult? So there are many reasons. Just to give some examples, the first one is the quantum computers has a hardware noise. So it has a high error rates in quantum operations, and also it is fabrication difficulty for the industry. The large chips are hard to build, and also the control complexity, like it requires thousands of control lines. So then it is difficult to build large quantum processors with millions of qubits. So it will cause a problem, limited qubit count for one QPU. So the large quantum circuits cannot be executed only on a single device. How to solve that? One of the potential way is distributed quantum computing. So what's a distributed quantum computing? What's the DQC? So multiple QPUs, they are interconnected to collaboratively execute a large quantum circuit. So we can see this figure just to show a brief, like a small quantum network. So like the red dot is QPU, and there are multiple QPU connected to a network. Give an example, okay, so now if we have a single QPU, its capacity is only 5 qubits. So now, like this network, it has 9 QPUs. So then 5 qubits will expand to the 45 qubits. So then it can solve the task with 45 qubits. So then DQC helps to expand the qubits number. As we say about the progress of the distributed quantum computing, DQC also has several challenges. Okay, here I show the challenge 1, the data privacy concerns. So now we just focus only on single QPU, okay? So for a single QPU, there are many quantum attacks, like the quantum membership inference attack and quantum crosstalk attack. So then I will talk more detailed about these two attacks. So the first thing is quantum membership inference attack. So the attackers want to know which quantum state served as a circuit input. I will give you an example, okay? So now we have an input, it's the original data set, and then we encoded, we assume the encoding map is norm and deterministic. And then it will encode it to the quantum state. For example, the input is rho A or rho B. And then it passes through the circuit. Finally, we can get two outputs. Output A is for rho A and output B is for rho B. And we can see that these two output distributions is easy to distinguishable. So if now the attackers observed these two outputs, it is easy for the attackers to infer the input is rho A or rho B. And because the encoded mapping is known, so they can the attackers can finally get like what's the original data set. And for the next attack, quantum crosstalk attack, it means like when an adversary circuit is physically coupled to a victim circuit, crosstalk can leak the victim circuit output. Also, I show you a figure, okay? So now we can see like, we assume that there are several users and they share the one QPU to do several tasks. And one of them is an attacker. So then, for now, if an attacker's circuit and attacker's qubit is neighboring with one of the user's circuit, and then the crosstalk attack may occur. So then the attacker's operations may affect the user's operations. I will give you a true example, okay? So for now, the users do the Groover's algorithm. And if there's no attacks, we can see the blue column, they can get the target final output. But if now here is an attacker and he will do in the Groover's algorithm neighboring qubits to do several remote gates. And then we can see the blue column will drop to the orange column. So then the user's output is changed. Also, I will talk more detailed about how the crosstalk attack can infer the true user's like output. So it has two phases, okay? The first one is reference phase. So attackers will record its own output distributions for the cases when the victim's output is 0 or 1. So what that means is now we have two circuits and there are two qubits, they are neighboring. And one is victim circuit and one is attacker circuit. The first thing is attacker will let the first qubit always be the output 1 or output 0. And then they will always observe their like attacker's result, and then will get the reference distribution 1 when the victim's output is 1, and also the attacker's reference distribution 2 when the victim's output is 0. And then it's the second attack phase. So also we can see there's like two circuits, they are neighboring. And then victims do its own circuit, and attackers do not know this victim circuit and also do not know the victim's output. But for the attackers, they can observe his own output, so they can get the attacker distribution 3. So for them, they can compare with the reference distribution to infer the victim's output is 0 or 1. Just to give an example, okay? So if the distribution 3 is more likely as the distribution 1, so they will infer that the victim's output is 1, okay? So then we can see like these two attacks may expose the like user's privacy input or reveal the true computational result. One intuitive approach is to intentionally disturb the circuit's output by injecting noise. For example, okay, now we add a noise, for example, the X noise. And then the output will tend to the perturbed output. And because for now, the attacker only can observe a distorted result rather than the user's true output. So then we protect the output and also then we protect the input. Here is a question. How should we define and quantify this injected noise and how much privacy can it provide? We use differential privacy. So before we talk about quantum differential privacy, first I give you some background about classical differential privacy. Okay, so classical differential privacy is to protect the privacy in classical computing. So it will learn the characteristic of the whole data, and the individual's data's privacy is preserved by adding artificial noise to the model. I give you an example to let you understand that. Okay, it's about like whether Alice submitted a paper. So now we have two data sets. One is with Alice and one is without Alice. So if we query these two data sets, with Alice tell you like the result is 3 people submitted a paper, but without Alice tell you like 2 people submitted a paper. So if the attackers can get these two outputs, it is easy for the attacker to infer that the Alice submitted a paper. So then Alice information is leakage. So what's the differential privacy do? Okay, so differential privacy will add noise into these two outputs, and then these two determined outputs will become two distribution and then perturb these two outputs and cannot infer the Alice information. And for DP, the probabilities of producing the same outputs are up to a factor of e to epsilon. So in this picture, in this photo, we can see just the maximum gap of these two distributions is e to epsilon. And also epsilon is very important parameter. It is called the privacy budget. It's to calculate the level of privacy protection. So if the epsilon is much smaller, and then it means the privacy level is much stronger. And then we can easily finally get the DP definition formula, and then we can extend to the quantum version. So how about content differential privacy? Okay, so like for the classical one, if we want to turn it into classical DP, the classical data set will be neighboring classical data set and pass through a random algorithm, and we add the classical noise, and then it will be like two similar classical output, and it's similar as the content. So now it turns to the content differential privacy. The input will be two neighboring content states, rho and sigma, and then we pass through the content operation big E. And then we will add the content noise, and with the measurement, finally we can get to classical output. So it's easy for us to get the content differential privacy, and we can see it is really similar as the classical differential privacy, but it adds several content parameters. And also, here optional is the privacy budget. And also, like in the previous study, QDP, it has shown to protect the user information on a single QPU. But distributed quantum computing, as we know, like several QPUs connected to be a network, is also vulnerable to these attacks we mentioned before. However, QDP may not provide sufficient tight privacy protection in DQC. So then here we get to challenge one. We need to find some new method to protect the privacy in DQC scenario. And then here is our challenge two we want to solve is the long execution time. So first, I still give you some background about DQC process. So now if we assume that, okay, we have a 4-qubit circuit, but we only has a QPU with its capacity is 2 computing qubits and 2 communication qubits. So it means that we need at least 2 QPUs to together to solve these tasks. And there are like many allocation ways. I just give you an example. Okay, for example, in this one, Q1, Q3 is allocated to QPU1, and Q2, Q4 is allocated to QPU2. And then we can see there are two types of CNOT gates. Okay, the orange one, we call it remote gate because it will execute across the QPU. And for the green one, we call it local gate because it can operate within one QPU. And it's worth noting that, okay, if we want to execute the remote gate, first we need to build generated and EPR pairs. So what is EPR pairs? So EPR pairs means the entangled qubits pairs shared between the QPUs that enable the content communication. Just in simple words, you can think this EPR pairs is built in between the communication qubits, and it seems like a communication channel to transfer the information from QPU1 to QPU2 or QPU2 to QPU1. Okay, and because the EPR generation process, it has some randomness, it has some errors, so it is probabilistic, loss limited. So we needed to do several times to build the EPR pairs. And also we can see table 1. EPR pairs preparation, its latency is far more than the single qubit and 2-qubit gates. It's needed to take about 2 microseconds. So that means remote gates is really time consuming because one remote gate need 1 EPR pairs. So then here is the challenge 2. So now if we have several remote gates in the like one distributed quantum computing process, and then it will lead to very long overall execution time. So also we want to solve this problem. Okay, so here is we talk about, we focus on the 2 challengers, and here is for my whole PhD study, what I'm doing. So like for the challenge 1, the privacy protection, I have 3 works. Okay, the first one is content differential privacy for the centralized privacy protection. And the work 2 is content local differential privacy for the local privacy protection. And then is content Renyi differential privacy for protect privacy in distributed quantum computing. And also, we can see for challenge 2, we want to solve DQC has long execution time. We want to reduce that. So we also have 2 works. Okay, one is called unique. We will give a generalizable and a scalable solution to reduce the execution time. And also for the work 5 is called JIL. We will use imitation and fine-tuning to further reduce the time. And For the first two work, I have discussed much detailed in the proposal. It's focused on a single QPU systems. So these two works is approved. So for today's, our topic is mainly focused on these other three works, and it is about the distributed computing systems. One is distributed DQC protection, and the other two works is about DQC optimization. Okay, so now let's talk more detailed for the work one, quantum Rayleigh differential privacy for DQC. So as we mentioned before, for a single QPU, we have several attacks, and based on my proposal, we already have two works to show that QDP and QELDP can protect the user information on a single QPU. But also for distributed quantum computing, each QPU remains vulnerable to these attacks. So, however, if we directly use the QDP into the DQC scenario, it may not provide sufficient tight privacy protection. So we need to find some methods. So the first thing is also I will give you some background in the classical computing, how to solve this problem, and then we extend it to the quantum version. Okay, so now we talk about if we add DP directly in the classical distributed computing. We can see there are several CPUs, and each CPU we use DP, and it will have epsilon 1, epsilon 2 to epsilon k, and finally we will get a cumulative privacy budget. And if we just focus on one CPUs, okay, epsilon 1, it's always, if we use the DP, it is the maximum of the total privacy loss. So it's always focused on the worst case. So then what will happen? It is easy for the privacy explosion because we will accumulate all the worst case together. So epsilon 1 is worst case, epsilon 2, epsilon k, they are all worst case. So for the researchers in the classical distributed computing, they proposed the RDP based on the Rayleigh divergence. And we can see there are very important parameters here is Rayleigh parameter, Rayleigh order, alpha. So if alpha is closer to 1, and then this one will become to a KL divergence. If alpha is closer to the infinite, and then it will become the DP. So it's focused on the worst case. So also now we just focus on one CPU. So for the RDP epsilon 1 prime, it will take an alpha order weighted average of all losses. It will smooth out the spike losses from extreme output. So we can tuning this alpha parameters by ourselves, so then we can adjust how strict the privacy guarantee is. And finally, we will get a smoother and tighter upper bound. Okay, so classical Rayleigh differential privacy based on the classical Rayleigh divergence, and also by tuning alpha, we can adjust how strict the privacy guarantee is. Then it's similar as quantum. We can propose the quantum Rayleigh differential privacy based on the measured quantum Rayleigh divergence. But we just add some quantum parameters here, but we just ignore this part. Okay, so also it's same. We also can by tuning this alpha parameter and adjust the privacy guarantee. Okay, so I just give you a very simple evaluation to show how the QRDP effectiveness. Okay, so now if we do a real algorithm on a quantum simulator, so for the QDP, we can finally get the cumulative price budget is 4.3, and for the QRDP, the cumulative price budget is 4.27. So we can see QRDP can get a much smaller privacy budget than the QDP. And if this is just a toy example, so if we do a very complex algorithm, and then this gap will be much bigger, so the QRDP can get a much tighter bound. And also I do analyze this QRDP under different mechanisms. For example, okay, the relationship between QRDP and the noise. So as the noise level increases, which means the noise increase, the epsilon will decrease. So it means the privacy budget will be much stronger. And also as the alpha, this Rayleigh order increase, the epsilon will increase because it will more focus on the worst case, because if alpha tends to the infinite, then it becomes differential privacy. Okay, so then for our first work, we can know that QRDP yields a tighter privacy bound in DQC and offering the stronger privacy protection than QDP. Okay, so this is just our very brief work one. Then we'll talk about the other two works. It's about the distributed quantum computing optimization. So the first thing is where the unified nonlinear integral programming. We want to solve challenge 2, the long overall execution time. So before we talk about our paper, we first give some background about the total basic DQC execution workflow. It has 3 steps, okay? So for the first step, qubit allocation, it's wanted to minimize the number of remote gates. I will give you an example to better understand that, okay? So now we also have a 4-qubit circuit, and we have only, each QPU only, its capacity is 2 computing qubits and 1 communication qubit. So now we need at least 2 QPU to solve these tasks. And there are many allocation ways. Just to give some examples, okay? So for the first way, we can allocate Q1, Q2 to QPU A, Q3, Q4 to QPU B. And for the second allocation way is allocate Q1, Q3 to QPU A and Q2, Q4 to QPU B. It's the same circuit, okay, but we can find that they are different. For the first allocation way, we will have 5 remote gates, but for the second allocation way, we have 2 remote gates. So as we mentioned, okay, remote gates is time consuming, so we will always will choose the second allocation way because it saves time. And then, okay, the second step, entangle the management. So it will establish an EPR pair through the communication qubit, which serves as a channel for information transmission. Here is our example as we mentioned before. So now for this circuit, we have 2 remote gates. And for each remote gate, before we executed that, we needed to build the EPR pairs between the communication qubit. So for these 2 remote gates, we have 2 EPR pairs. And then is the network scheduling part, the last step. Remote gates without qubit overlap can be parallel execution, otherwise executed sequentially. Okay, also for this work, okay, for this example, we can see there's 2 remote gates, but these 2 remote gates has a qubit overlap, Q1, right? So these 2 remote gates can only be executed sequentially. So it means we first need to do the remote gate 1, and after that, do the remote gate 2. Okay, so now we know the 3 steps of the basic process of DQC, and the existing works, they have to do some progress to reduce the execution time. For example, the reference 1, for the qubit allocation part, they use the graph partition to minimize the remote gates. For the network scheduling, they use the priority-based scheduling. Also, an example, okay, so now we have 2 remote gates. They will do it in sequentially. First, they will do EPR pair 1 and have the remote gate 1 will execute it, and then do EPR pair 2, and then do the remote gate 2. Based on the table 1, as we mentioned, for this circuit, it will take about 4 microseconds. Then it has some disadvantages, okay? So we can see it in this work, it processes these 3 steps sequentially and independently. And also, they do not consider the parallel gate execution. And then what about the next work? Okay, so another work, they do some progress on that. Okay, they will generate the EPR pairs in parallel to save execution time. Okay, so for the reference 7, we can see that if there's sufficient communication qubits, so then they will, in just 1 EPR time, to do these 2 EPR pairs together, and then do the remote gate 1, and then do the remote gate 2. So then for this example, for this case, we can see the total time becomes 2 microseconds. So it saves time, right? But it still has a disadvantage for this work. We can see the first one is still every 3 steps independently. And the design is highly architecture dependent, requiring the circuit by circuit analysis. We will talk it much detailed in next page. So for our work, we will formulate the joint optimization of 3 steps as a nonlinear integer programming problem, an IP problem. And we also will generate the EPR pairs in parallel, but we will give a generable framework for arbitrary networks, and then it is easy to scale up. Okay, we give some more details to compare our work with reference 7. So reference 7, they will give many circuit rewriting rules for parallel EPR preparation. What that means? Okay, so it means like for different circuits, they will give you different circuiting rewriting rules to transfer the circuit, and then these circuits can do the parallel EPR preparation. It is rule-based and circuit-by-circuit optimization, so it has a very big disadvantage. It's limited generalized and scalabilities. So our work will just give one generable and scalable solution. We have 3 steps. Okay, so first we will formulate as a unified optimization problem and design an algorithmic solution, and finally generate the execution plans for arbitrary circuits. Okay, so what that means? Still for different circuits, but we will only use one overall framework to solve these problems. So we will give a unified mathematical way. So then it will applicable to arbitrary circuits. Okay, so that is our mathematical formulation part. So how we formulated the DQC problem, okay? The first is the objective function. Okay, we will minimize the total execution time and also minimize the communication cost. And we have 9 constraints. I will talk it detailed in one by one. Okay, so first one is mapping validity. So it means like each logical qubit Q must be assigned to exact 1 QPU. Example, okay, so now we have 4-qubit circuit, and then we can allocate Q1 to QPU A, Q3 to QPU A, Q2 to QPU B, Q4 to QPU B. So each logical qubit needed to be allocated into a exact QPU. And there is a QPU capacity. So the number of allocated qubits QPU U cannot exceed its capacity. So also this example, so now we have a QPU with capacity only 2 computing qubits. So only the maximum logical qubit can be allocated is 2. And there is a gate scheduling. So each gate must be and can only be assigned in an exact time slot T. So it means that like we have several remote gates, but each remote gate needed to select the one time slot to be executed. And then is the same QPU indicator. So it means like whether 2 qubits of single gate is reside on different QPUs. It's very simple. Okay, so it means that if it is local gate, so then the delta equals 0. So if it is a remote gate, it cross the QPUs and then delta equals 1. And for the constraint E is the EPR generation requirement. So it means that if you are a remote gate, you definitely need an EPR pairs. So we can also see for this example, the sum of Y is 0, and for the remote gate, the sum of Y is 1. So it means it needs EPR pairs. And constraint F is the EPR before the execution ordering. So the EPR pair of the remote gate must be generated before the gate is executed. Also, I'll give an example. Okay, so now we have 2 remote gates. So the EPR pairs for these 2 remote gates must be generated before the time slot or in its time slot. So before the gate execution. Then it's a precedent. So if 2 signal gates have qubits overlap, they have execution order. So here is example. So now we have 2 signal gates. We can see there's a qubits overlap, Q1. So it means we first need to do the first gate and then do the second gate. And then it's constraint H, undirected mapping indicator. So it means a dummy variable, theta GUV indicates whether gate G spans QPU U and V. Okay, the same. For the local gate, theta GUV equals 0, and for the remote gates, theta GUV equals 1. Also, we have constraint I. It's about the concurrent EPR generation and inventory, because we know that the EPR pairs can be stored and used subjected to the inventory limits. So this constraints will help you to, like, for each time slot to calculate the total number of EPR pairs remained. Okay. So then, because we formulate the DQC problem as a nonlinear integer problem, so it is NIP problem. So it is a NP hard problem. So how can we solve this NP hard problem? In our method, we use the two-stage heuristic approach. Okay, so the DQC stage we formulated as a unified NIP, and then we know it is hard to solve because exact solving is computational prohibitive. Then here is our method, our algorithm. So we use the two steps. One is called greedy mapping, and one is called JIT scheduling to decompose into mapping and scheduling decisions. Okay, so then for the first one, what is mapping? So placement determines like whether a CNOT is local or remote, and mapping is the spatial decision that reduces the communication cost. So we will map the qubits with strong interaction weights in sync-QPU, and then we will get the fewer remote gate and then has the less EPR demand to get the less execution time. Here's the example. Okay, so for this example, we can see Q1, Q3, they are strong interaction, right? Because they have three remote gates, three CNOT gates. Okay, so then we will allocate Q1, Q3 to QP1 and allocate Q2, Q4 to QP2. Next question, okay, is what is JIT scheduling, just-in-time scheduling? So gates and EPR pairs must satisfy the precedence and communication qubit budgets over time, and scheduling determines when to execute each gate to finish the circuit as early as possible. So we will schedule each gate in the earliest feasible slot and generate the EPR pairs in slot or earlier when beneficial. So then we can finally get some kinds of execution plans. Just in summary, okay, so for the algorithm input is the circuit, QPU topology, and capacities. And then we have two stages. For the stage 1 is the greedy map qubits using the interaction weights. And for the stage 2 is the scheduled gates in earliest feasible slots. And we will attribute the EPR pairs. And then the final output will become a feasible execution plan with lower runtime and communication cost. That's our evaluation part. Okay, so here is our evaluation settings, and we will test our method in several circuits. The circuits with 4 different scales: the tiny circuit, small circuit, medium circuit, and large circuit. And also we will do some experiments on the real-world quantum circuit shown in table 3. And then we have some evaluation metrics. There are 4. One is circuit runtime, and one is algorithm execution time, and one is the objective value defined in the equation 1, as we mentioned, and the EPR pairs utilization. So we will minimize the first 3 metrics and maximize the EPR pairs utilizations, and then we can get a better performance. And also we have some baseline methods. Okay, we have 4. One is simulated annealing, so it is a heuristic global optimization, and one is a random. We do the DQC process in a random mapping, and the third one is average. We will average over the random trials, and finally is the cloud QC. It is an existing works. Okay. So first evaluation is we test our circuits on the different user-defined circuits: tiny circuit, small circuit, medium circuit, and large circuit. And we can see our algorithm compared with the other 3 methods. And the blue block is our method. And we can see that our method achieves the lowest objective value. So it means it indicates that our method gets the shortest circuit runtime. And also the next figure is the algorithm execution time. We can see also the blue block is our algorithm. Compared with the other ones, our like algorithm execution time is accessible, but like simulated annealing, it takes a lot of time. And then as a framework comparison, we compared our work with Cloud QC. So we can see that for the first one, we can always achieve the lowest objective value, which means it indicates the shorter circuit runtime. For example, in this, we can see if we do the Cloud QC and our circuit in a scene case, and for the Cloud QC, its objective value is 2000. For our method, our objective value is only 1000, so it's far less than Cloud QC. And for the next figure, it shows that we can achieve the shorter circuit runtime than the Cloud QC, the blue blocks. And for the figure D, we can see compare with the algorithm execution time, our method is also shorter than the Cloud QC. Then we can get our second work, very important results is conclusion is unique, can further reduce the communication cost and the execution time. So that is our work 3. So it is also about the DQC optimization, but we will wear the general attention and the reinforcement learning. So also we wanted to solve challenge 2 because DQC has long overall execution time. So as we mentioned, okay, for our second work, there are some strengths of our second work unique. So the unique will formulate the DQC as a unified optimization problem, and it will jointly optimize DQC 3 steps. And also it will provide a good heuristic solutions. But it will have some problems, okay? So the first thing is we can see the unique solution is still we use the heuristic method, so it still has far away from the global optimum. And also, if we use some state-of-art existing methods like heuristic search method, like simulated annealing, it may help us to find some better solutions, but it gets computationally expensive and slow. So for our third work, our goal is to find a faster approach to obtain the better solutions. So for our third work, we inspired from the AlphaGo. So AlphaGo has 2 steps. One is the imitation learning, one is fine-tuning. So for the imitation learning part, the AlphaGo will first learn the basic rules, learn the human gains, and then imitate the expert strategies. And then for the second step, fine-tuning, they will discover the strategies beyond the experts and use the reinforcement learning. Finally, they can beat the human players. It is similar as our third work, okay? Our approach also has 2 steps. One is imitation learning. We will let the unique solution, the second work solution, be the expert data set. And then use imitation learning to imitate the expert strategies. And the second step is fine-tuning. So we will find some strategies beyond the unique solution. And finally, we can get the execution plan better than the unique, better than the second work. Also, another advantage of our work, our third work, is offline training and online inference. What that means? So for the training phase, it's extremely computationally, so it takes maybe longer time. But for the inference phase, it's extremely fast, which means if now we have a new user, they want to use our method, we can give them an execution plan just in I think few seconds. Also, here is our GI workflow. We have 5 steps. So now I just do it one by one. So first, for the first 2 steps, for the first step, reformulate the unique solution as an NDP. So we will convert the unique optimization, the unique result, into a step-by-step process. Step 1 is state action, step 2 state action, step 3 state action. And the second step is we will represent the whole DQC problem as a graph. We will build a heterogeneous graph from the circuit, qubits, QPUs, and their relations. And that is the next two steps. Okay, for the third step is we wanted to encode the graph state. So we will use IGCN. It is one of the GNN variants to determine the relationship between the node and edge in the graph. Okay, and then extract the graph features for the decision making. And for the first step is we will score and select an action. We will use attention to evaluate the actions and choose the best action for each state. And finally, the fifth step is update and learning. So we will execute the action, get rewards and next state, and then train the policy with imitation learning and PPO reinforcement learning. Okay, so now we have 5 steps. We'll talk it more detailed. First, like before we talk about our work, still I give you some background about this. Okay, the first is what is GNN? I think you are familiar with that, so I just do it very quickly. So graph neural networks are a type of neural network designed to learn from graph structured data by leveraging the relationships between nodes. It has 2 components. It has 2 elements. Okay, the first is nodes. It represents the entities like qubits. And another one is edges. It will represent the relationships or connections. And then here's the basic steps of the GNN, how to capture the graph structure and node features. I'll give you an example to understand that. So now here we have 4 nodes. Okay, each node has its own features. And node 1, node 2, node 4 is the node 3 neighboring like nodes. And then for the second step, we will aggregate the neighbor information. So for the node 1, 2, 4, its neighboring features, we will add it together to be a new neighboring features. And then for the third step, the aggregated neighboring features and also our original node 3 features will pass through the neural network, and finally will update the node 3 features. Okay, also some background about what is reinforcement learning and attention. I also think you are familiar with that, so I will do it very quick. So for the reinforcement learning, it means like an agent learns to choose actions through trial and error by interaction with an environment to maximize the cumulative rewards. I think you are familiar with that. So we have 4 key elements: the state, the action, the reward, and the policy. And also for the attention mechanism, so we will allow a model to focus more on the most relevant parts of the input by assigning different weights to different information when making a decision. It also has 3 key elements, okay, the query, the key, the value. So just in simple words, attention will based on each state to help the users to select the most match action for this state. So then we will talk more detailed about our 5 steps as we mentioned before. Okay, so our third work, GARL, it still solves the same questions, the long execution time. So it will use the same mathematical formulation as our second work. So we will ignore that part. And the step 1, from unique solution to the NDP trajectory. So we will convert the final unique solution into a sequence of state action pairs. So at each step, the agent will observe the current state, takes an action, and moves to the next state. So also, as we mentioned, it has 4 important parameters. Okay, one is elements. For one is the state, it is the current system status, and one is action. So for our problem, we have 2 actions for each state. They can do the value mapping or they can do the scheduling decision. And then is the transition, and finally is the reward. I will give you an example to better understand the NDP trajectory. Okay, so now if we assume that we have an initial state S0, And we have two logical qubits, the Q1, Q2, and we have two QPUs, U1, U2. And here is one CNOT gate between the two logical qubits. And the state representation is HT is the graph containing the gates, qubits, and QPUs. WT is the system resource status with the the capacity, like the entangled bandwidth. Okay, so here is an example to show the initial state. We have two qubits, one CNOT gate, and two QPU. And then here is the first step action. We will map the logical qubit Q1 to the QPU U1. So then the state will update. We will add a mapping edge Q1 U1 and reduce the available capacity of QPU U1. And then is our action 2. Okay, so we also will do the mapping. So now we will map the logical qubit Q2 to QPU U2. So then we also will get some result. For example, now for the gate G, the CNOT gate, it becomes a remote gate because it's cross the Q1, Q2 is cross the QPU, and also the inter-QPU communication will be required. We need the IPR pairs before we do the remote gate. And then the scheduling action, okay. So for this one, it means that now we want to schedule the gate to execute at time slot 5. So then also the state will update. So then the gate, this CNOT gate will removed from unscheduled set, and also communication resources are consumed, and the system completion time may increase. Okay, so here we will use the reward to evaluate each step's action is good or not. Here is two parts of our reward. One is called extend. It's the penalty if execution extends the total completion time. And one is com. It is a penalty for inter-QPU communication cost. And also we have our objective. So the IR agent learns a policy to maximize the cumulative reward, which corresponds to minimize the execution time and the communication cost in DQC. Okay, so what that means? So now, if we want to know step 2 action is good or not, the step 2 objective is step 1 reward add the step 2 reward, and then we will maximize this cumulative reward. So now we know that NDP can break down the unique final composition into state action, state action, state action. Next problem is, how does the model understand this state? Okay, so now the next step is we use the RGCNN. So here is a problem is we want to joint mapping and scheduling. So DQC tasks are coupled and dynamic, and mapping will affect the qubit placement, and scheduling depends on the resource status. Here is some conventional approaches. For example, if we use the greedy heuristic as the second method, the second work, the unique, it's still focused on the local decisions. So now we think about we wanted to represent the DQC process in a GNN. Okay, but we cannot directly use the standard GNN because it treats all edges with the shared weights. So it's not ideal for DQC state with multiple relation types because it has multiple entity types like gates, qubit, QPUs, and multiple relation types like dependency and mapping topology. So here is our solution. So for the step 2 and step 3, we will use the heterogeneous graph and RGCNN. So we will construct a heterogeneous graph from the current DQC state and use the relation specific message parsing across the different edge types. And then we will produce the suitable actions for mapping and scheduling. So then the state graph will tend to extract the graph features. So RGCN will let the different edge types use different transformations, so the model can preserve